Hey everyone, let's take a look at your third practice test of the semester. This is covering the Chapter 7 content, Section 7.1 through 7.7. This is probably the most important test of this semester. As you know, there's some pretty complicated and sometimes long integration problems within Chapter 7, and these are integration skills that are going to be needed in future classes. The breakdown of the test should be just like I do on this practice test. Please notice I've tried to go in order of the content that we've had in Chapter 7. The first 4 questions here are all out of Section 7.1. They all involve integration by parts. Of course, whenever you're doing a problem with integration by parts, sometimes you'll maybe do the cycle method or have to do a substitution within the integration by parts. Please notice I'm trying to be kind on these first 4 problems. I tell you specifically what techniques are required in the problems and even the order in which it's required in 1 and 2. And then number 5 and 6, those are straight out of section 7.2, are techniques of trig derivatives. And then 7 and 8 is trigonometric substitution. That's section 7.3. And then my favorite section of the semester, 7.5, that's the method of partial fractions. That's problems 9, 10, and 11. And then 12, 13, and 14, those are problems that you're going to have to determine the best techniques. So unlike the first set of problems where I broke it down, where the first 4 integration by parts, 5 and 6, integration using our trig derivatives, and then trig substitution in 7 and 8, partial fractions 9 through 11, 12 through 14, you're going to have to decide what method is best in those problems, the same way that we had to do in section 7.6. And then finally, the last 3 problems, fairly simplistic problems, where I will be looking at your notation more so than anything. The integration itself should not be a struggle in problems 15 through 17, but that section was all about improper integrals and using correct notation in order to put them in proper form. So yeah, I'll be looking for a correct answer, but more importantly, in 15 through 17, I will be looking to make sure you used the proper notation in those problems, because all of these integrals are in improper form, either because they have an infinite limit of integration or because they have a limit of integration where the function is undefined at, and we have to put that into proper notation. Okay, so heading on into looking at this practice test with you, let's take a look at what I did for the first problem here. So problem 1 in the instructions told us to use integration by parts and then substitution to find this integral of the inverse tangent of 2x with respect to x. Okay, so using integration by parts, we know that we let u equal liate. The second letter in liate is inverse trigonometric function. So you say, well, okay, I'll let u equal the inverse trig function. And then that means everything else in there, which is dv, has to be dx. Okay, now the derivative of the inverse tangent of 2x. I know that the derivative of every single inverse tangent function is 1 over 1 plus whatever's inside of it, quantity squared. In this case, that becomes 1 over 1 plus the group 2x squared. Well, the group 2x squared gives me a 4x squared down there. So this is the derivative of the inverse tangent of 2x. Then I have to remember, chain rule says times the derivative of what was inside of that function. That's where the times 2 comes from. And then we know that this derivative is with respect to x. When I integrate 1 with respect to x, I get my x. So now I have my u, my v, and my du. I'm ready to set up my integration by parts formula. I can say that the original integral is equal to u times v minus the integral of v times du. So u times v, that gives me x inverse tangent of x Typically, we put the algebraic before the inverse trig function in notation. It doesn't really matter, but that's my u times v, and then minus the integral of v du. I went ahead and pulled this factor of 2 out front, and I said minus the integral of 2, and then when I multiply this x on top of this group 1 plus 4x squared, I have the integral of x over 1 plus 4x squared with respect to x. At that point, I knew that this was a simple substitution problem for a couple of reasons. I specifically said that you would need to use integration by parts and then substitution to integrate this. So the substitution here, I would let t equal that denominator, 1 plus 4x squared. And then I can say, well, then dt needs to equal 8x dx. I need an 8 in that numerator. So I can say, well, all right, if I put an 8 up there, then I would have to divide by 8 on the outside. You'll see in the next step, that's where that 2 over 8 became 1/4. And then that 8x dx just became dt in the numerator. My denominator was t. So clearly, that's going to integrate to be the natural log of t. I have x inverse tangent of 2x minus 1/4 the natural log of the absolute value of t plus the constant of integration. Now we need to put our answer all back in terms of x. So you say, well, okay, here's where you just say we know t is the group 1 plus 4x squared. So then we can go in here and say it's x inverse tangent of x minus 1/4. And since I know 1 plus 4x squared is guaranteed to be positive, you don't need the absolute value. It's no big deal if you put an absolute value, but you don't need it. And I can say minus 1/4 natural log of 1 plus x squared plus c. That final answer, x inverse tangent 2x minus 1/4 natural log of 1 plus 4x squared plus the constant of integration, that's what I'll be looking for there. Now, notice in the next problem here, I tell you to use substitution and then integration by parts to find the integral of this function. And there's a lot of natural logs in there. It's easy to get confused. So whenever you think about using substitution, substitution says your typical choice for you is whatever's the innermost term inside your integral. Well, clearly the innermost term is what's inside of this group. And I can say, well, it's the group of the natural log of x. It's the argument within this natural log. So I can say, all right, I'm going to let the natural log of 3x be equal to t. Now, the reason I didn't do a u substitution is because I knew after I did substitution, I would need to do integration by parts. And integration by parts would involve a u, so it would get confusing if I did a u substitution here. So I said, all right, let's let t equal the natural log of 3x. Then I can say that dt, the derivative of any natural log, is 1 over what's inside of it times the derivative of what's inside of it. That would give me 1 over 3x times 3 with respect to x. That just, the derivative of the natural log of 3x simplifies to simply be 1 over x dx. And that's actually fantastic because I have a 1 over x dx in the problem. So I can say this substitution is clearly going to be possible. The 1 over x dx becomes dt. And then this is going to become the natural log of t times t for the inside. Now that natural log of t times t, I would rather write the t out in front, so I did, but please make no mistake, this is where the natural log of t is coming from. The last term is where the factor of t is coming from. But I can say, all right, order of multiplication doesn't matter, but it looks better to say t natural log of t dt. Then I'm thinking, okay, integration by parts. Integration by parts says I'll need to let u equal Liate. The first letter of Liate is natural log. So I let u equal that natural log of t. Everything else in there is dv. T natural, t dt is my dv. Then I can say, okay, the derivative of u is just going to be 1 over t dt. if I integrate t over here, the integral of t is just power rule. You'd say it's going to be 1/2 t squared. So I can say then the original problem should equal the integral of this function, which is equal to u times v. That's going to be the natural log of t times 1/2 t squared, better written as 1/2 t squared natural log of t. And then it's minus the integral of v du. So when I thought about that, I said, well, I can go ahead and factor that 1/2 out. And then t squared times 1 over t is going to leave just a t to the first inside the integral integrated with respect to t. Now the integral of t with respect to t would be t squared over 2. That means that that last term is going to become minus 1/4 t squared. So I'm done with this problem, at least with respect to t. I can say with respect to t, my answer is 1/2 t squared natural log of t minus 1/4 t to the second plus your constant of integration. At that point, you just remember that t is simply the natural log of 3x, and then you rewrite your final answer. 1/2 t squared becomes 1/2 the group natural log of 3x quantity squared, times the natural log of t becomes times the natural log of the argument, the natural log of 3x. And then I have minus 1/4 times the group, the natural log of 3x quantity squared, plus the constant of integration. I would need to see that for your final answer, and that would be gorgeous. The next one, and please note, tell you it's a cycle problem. Integration by parts cycle method, anytime you have an exponential and a trig function, you know neither one of them is ever going to simplify when you take the derivative. It's going to keep on being an exponential function and keep on being a trigonometric function no matter how many times you take the derivative. But what the cycle method tells us is that if we use integration by parts on it twice, it should cycle back around to where we have what we're originally trying to solve for on both sides of the equation. And that's actually a good thing, because then at that point we can solve for it algebraically. So that'll be the process in this problem. So looking at number 3 here with you, I can say, all right, I have the integral of e to the 2x sine of 5x dx. When I'm thinking u, set u equal to Liate, I know that my trigonometric t comes before the last letter in Liate, e. So trigonometric function comes before exponential function. I'll set u equal to the sine of 5x. Then dv has to be everything else, the e to the 2x dx. I take the derivative of u. Well, the derivative of sine is cosine. The derivative of the sine of 5x would be the cosine of 5x times 5. Again, remember that 5 comes from the chain rule times the derivative of the inside. Now, of course, I have to put dx. This is my derivative with respect to x. When I integrate e to the 2x with respect to x, I just say, well, the integral of any exponential function is that exponential function divided by the derivative of its linear exponent, which is where the 1/2 came in there. So now I have all of the first part I need for the first use of integration by parts. So I'll say then my original integral is equal to u times v. U times v, that's going to be 1/2 e to the 2x sine of 5x. And even if you didn't know to write the exponential function first, we should see from the format of the problem, it's superior to write the exponential function before the trig function. Now, obviously, order of multiplication doesn't matter. So if you wanted to write u times v as the sine of 5x times the group 1/2 e to the 2x, that's okay. It just doesn't look as clean as this. So u times v, I would rather say v times u and put the exponential first. Now, minus the integral of v du. Minus the integral, I'll go ahead and factor out the constants and say that 5 over 2 is going to come out in front. And then I'll have the integral of e to the 2x cosine of 5x dx. And at this point, anytime you're using integration by parts, you should look and say, did integration by parts help? Is what's left easier than what I started with? And the answer to that is no, it's not easier. It's the same level of difficulty. But then if you just understand that, oh, one more use and I'll work back around to the original and then be able to solve algebraically. Okay, so I do that. I say, here's the integrand I still don't know how to work with. I'll let u equal the trig portion, the cosine of 5x, dv be everything else, the e to the 2x dx. Derivative of cosine is negative sine, so the derivative of the cosine of 5x is going to be negative 5 sine of 5x with respect to x. When we integrate dv, we'll get our 1/2 e to the 2x. Then I can come down and say, all right, then the original problem, the integral of e to the 2x sine of 5x dx is equal to the 1/2 e to the 2x sine of 5x I already had, and then minus 5/2 times the group, and then this is the part we just use integration by parts on, so I can say minus 5/2 times the group, u times v, that's my 1/2 e to the 2x cosine 5x right here, and then minus the integral of v du, but I can see that the constant coefficient I could factor out is going to be negative. So instead of minus the integral, I said plus the integral of 5/2, and then I'll still have my e to the 2x times the sine of 5x dx in there. Now at this point, what I needed to see was that the first two terms that I have on the right-hand side, they have to stay on the right-hand side. But this last term here, please understand that this is going to be a minus 25/4 times the integral of e to the 2x sine 5x dx. So I need to move that with the other integral of e to the 2x sine 5x dx. And again, keep in mind, when you distribute that negative 5/2 through, this last term would have a coefficient of negative 25/4. So I said, let's add 25/4 times that integral to both sides. Please understood, you already had an understood 4/4 on the left-hand side. So you say 4/4 plus the 25/4, that gives me 29/4 times this original integral. And now my right-hand side just has these two terms, the 5/2 times 1/2, that gave me a minus 5/4 e to the 2x cosine 5x. And whenever you get the whenever you get the integral all on one side, the other side needs to have the constant of integration brought into the problem. So I had to add plus c at this part. That had to be introduced here. Now I can say, well, all right, my goal was to solve for the original problem, not 29/4 times the original problem. Then we just say, okay, then the original problem is just when we multiply by 4/29 on both sides. And when I multiplied by 4/29 on both sides, that gave me 4/29 times 1/2, that's 2/29 e to the 2x sine 5x. And then 4/29 times 5/4 gave me, and I knew it was already subtracting, minus 5/29 e to the 2x cosine 5x plus c. I'd be completely happy with that answer. And then you can see I also did a factored answer here too, which you can certainly do, but don't feel obligated to factor. There's no need in that, but it's cool. Up next, for the fourth problem, and this is our last of the integration by parts problems, at least those that we know involve integration by parts. It's the last of them. Number 4, I'll give you an integration by parts problem in where we have a definite integral. So we said, okay, now again, notice in the directions, unlike the first 3 where they were kind of two-part problems, integration by parts and substitution and integration by parts. And then we had to use the integration by parts cycle method, which means we had to use integration by parts twice and then solve algebraically. The solution procedure in this one is going to be much quicker because we just use integration by parts. But then once we use integration by parts, I want you to evaluate the definite integral. And obviously, I want you to show your work. And I would expect an exact and an approximate answer, because I don't want you just going to your calculator and hitting math 9 and coming up with this and saying, yeah, I solved it. That would be terrible. You could check it that way, but you can't do it that way. So for number 4 here, you look in here and you see what we have: a product, an algebraic function x times a natural log of x. Clearly, u equals Lyaute. L comes before I in Lyaute, so we'll let u equal the natural log of x. That means everything else in there, which is your x dx, has to be dv. We differentiate the natural log of x to get 1 over x dx. We integrate x to get 1/2 x squared to solve for v. Then we can say, all right, then this original integrand evaluated from 1 to 8 is equal to the expression u times v. And please notice the notation I'm using here is what I would want you to do. You just do evaluation brackets and show that everything's going to be evaluated from 1 to 8. And the first part of that, of what's being evaluated, is your u times v, 1/2 x squared natural log of x. Again, I knew I wanted to write the algebra before the natural log to keep the order that was within the original problem. So I have 1/2 x squared natural log of x minus the integral of v du, which becomes minus 1/2 the integral. And I would just have an x in there with the dx when the x squared cancels with the 1 over x and leaves me x to the first power in there. Now, obviously, that's easy to integrate. The integral of x is going to be 1/2 x squared. That 1/2 comes out and multiplies the 1/2 that was already out in front. And that's going to simplify to give me the expression 1/2 x squared natural log of x minus 1/4 x squared. We then evaluate the expression from 1 to 8. When I plugged in an 8, I had 64 times 1/2 is 32. Natural log of 8 minus 1/4 times 64, which gave me my 16 there. So all of this evaluated at 8 gave me this part. Then I say minus the lower limit. When I plug in the lower limit, though, you don't get much, because we know that the natural log of 1 is 0. That's where the first term came from there. Minus 1/4 times 1 squared, that's minus 1/4. So my lower limit evaluated to just be a negative 1/4, but of course we subtract the lower limit, so that's actually adding 1/4. So when I did this, I just said, well, it's going to be 32 natural log of 8. That's the irrational part. And then the part that has a decimal answer, or fractional answer in this case, rational answer, I could say I have a negative 16, which is the same thing as negative 64 over 4. We're adding 1 over 4. Negative 64 over 4 plus 1 over 4 gave me a negative 63 over 4. So the great exact answer that I would be looking for is that right there. And then, of course, the decimal approximation to that, 50.792 there. Now for the next one, whenever we're looking at our trig integration problems, I want you to be familiar with what do we do when we have an even power of sine or an even power of cosine. And the quick answer to that is you have to use your power reduction formulas. Your power reduction formula for cosine squared is going to be 1/2 times the group 1 plus the cosine of twice the angle. The power reduction for the sine squared is 1/2 times 1 minus the sine of twice the angle. So in this problem, before I even worried about the integral, I just said, let's go ahead and use our power reduction formulas to get this sine function to be down only to the first power. So I said, okay, the sine function power reduction formula, please notice the power reduction formula, whether it's the cosine power reduction or the sine power reduction, puts it in terms of cosine. Please don't get confused with that. So I can say, well, all right, I know that sine squared of x is going to equal 1/2 times 1 minus the cosine of 2x. So that's what I did. I said, well, the sine squared of 8x would be 1/2 times 1 minus the cosine of twice the angle, which gives me 1/2 times 1 minus the cosine of 16x. This would equal to sine squared of 8x, but we had sine to the fourth, so we have this group squared. When I square out that group, I can say, well, all right, then I have 1/2 squared. That's where the 1/4 came from. I also have this group 1 minus cosine 16x squared, so I multiply that out. I get 1, and then I would have minus the cosine of 16x minus the cosine of 16x minus 2 cosine of 16x, and then you would have a negative cosine of 16x times a negative cosine of 16x. That's where the cosine squared of 16x came from. So one use of the power reduction formula does lower the power from 4, but we still have a second power in there. That's not allowed. I don't know how to integrate the cosine squared. So I use the power reduction formula again. This term's absolutely fine. Of course, the constant's fine. So I rewrite the rest of the problem. And then this last portion where I had the cosine squared of 16x, I can say, well, okay, power reduction formula says that that's equal to 1/2 times the group 1 plus the cosine of twice the angle. 1 plus the cosine of twice the angle gives me 1 plus the cosine of 32x. Okay, now at this point, I just need to simplify. My constants in here would combine to be 1 plus 1/2. That combines to be 3/2. I brought down my minus 2 cosine of 16x, and then I would also have a plus 1/2 cosine of 32x. So after using the power reduction formula twice, we've taken our 4th degree trig function to make it a trig function with only first degrees. Now, of course, it's in terms of cosines now. So I have to say then the original integral that I asked you to do here in number 5, the integral of the 4th power of sine of 8x with respect to x, that integral is equal to 1/4 the integral of 3/2 minus 2 cosine 16x plus 1/2 cosine of 32x. Then I can say, okay, then I can integrate this, leave my factor of 1/4 on the outside. The integral of 3/2 is just 3/2x. We know that when we integrate cosine, we're going to get a sine. So minus 2 cosine of 16x becomes minus 2 sine of 16x divided by the derivative of this angle, 16. Remember, whenever you're going in reverse, you have to do the chain rule. You say, yes, I can integrate the trig function, but I also have to divide by the derivative of that linear angle. And so that's where the division of 16 comes in here. 2 divided by 16 is where I got the minus 1/8 in front of that. And then the last term here, again, integrate cosine, you'll get sine. This is going to become plus 1/2 sine of 32x, all divided by 32. 1/2 divided by 32 gave me 1/64, the sine of 32x. And then at that point, I would be actually happy with this answer right here. You could have circled that. The only thing I've done from here to here, obviously, is I distributed through my 1/4. I actually kind of like it better left factored out. But either way there, you would have your correct final answer. Now, for number 6 on this test, what I'm wanting you to remember is that whenever you have multiple terms in there or multiple trig terms in there, how do you know which one to work with and which one to avoid? And what you're supposed to remember is that we want to work with odd powers of sine, cosine, tangent, and cotangent. We can work with those odd powers. We rewrite all but one power in terms of another trig function and then use a u substitution every time. With secant and cosecant, you want even powers of them, and you want to rewrite all but 2 powers as another trig function. So in this problem, there's no question which one that you're going to attack. The secant's to an odd power. I don't want to work with that. The tangent's to an odd power. I do want to work with that. Odd powers of sine, cosine, tangent, and cotangent, You attack them. So I can say, okay, I will attack the tangent to the 5th power. When I say attack the tangent to the 5th power, here's what I mean. Just like I was saying, you rewrite all but one power as another trig function. So I'm going to say tangent to the 5th is the same thing as tangent to the 4th times tangent. Tangent to the 4th is the same thing as tangent squared, quantity squared. And then one of your Pythagorean identities says that, well, tangent squared is the same thing as secant squared x minus 1. So I can say, well, all right, then tangent to the 5th x is the same thing as secant squared x minus 1 quantity squared times the tangent of x. If I ask you to square out secant squared x minus 1, which it's probably wise to go ahead and do, you can say that's just going to give me secant to the 4th x minus 2 secant squared x plus 1, and again, times that leftover tangent function. How does this help solve the problem? This original problem of the integral of the tangent to the 5th secant cubed, I can say tangent to the 5th is equal to this trinomial in terms of secant, and then times the secant cubed x that I still had there, times that remaining factor of the tangent to the 5th, the first power of tangent, I'm sticking that on at the very end. Now, the whole point to attacking this tangent and rewriting all but one power in terms of secant, from the very beginning, as soon as I did this, I knew I was eventually going to use the trig substitute, or I shouldn't call it a trig substitution, the substitution of a trig function of letting u equal the secant of x. I'll do that now. If u is equal to the secant of x, we know that the derivative of secant is secant x tangent x dx. So this is telling me in order to do this substitution in this problem, I have to have a factor of secant x and a factor of tangent x dx in order to substitute in my du. Well, I do. I have secant cubed tangent x dx. So one of the powers of that secant cubed and that tangent x dx all go away and become du in the next step. But there's going to be a secant squared left there that doesn't get taken with the du. So you say, well, that secant squared is just going to become u squared. And then my secant formula here, secant to the 4th minus 2 secant squared plus 1 becomes u to the 4th minus 2u squared plus 1. At this point, we have a pretty nice, easy integral to do. But before you can integrate, you have to first do the algebra. So I distribute the u squared through this trinomial, and I get u to the 6th minus 2u to the 4th plus u squared, all integrated with respect to u. And then we can say, well, okay, now it's just power rule. U to the 6th becomes u to the 7th over 7. 2u to the 4th becomes 2u to the 5th over 5. And u squared becomes u to the 3rd over 3. Of course, the second term is still subtracted since it was subtracted on the inside. Whenever you're going back in, and you can say, well, we know that u is equal to the secant of x, so my final answer would just be 1/7 secant of x to the 7th power minus 2/5 secant of x to the 5th power, and plus 1/3 the secant of x all raised to the 3rd power, plus your constant of integration. All right, now those were problems involving trig functions whenever we integrated. And so our techniques there, if I give you a sine or cosine to an even power, you know you need to know the power reduction formula before trying to work the integral. If I give you a sine, cosine, tangent, or cotangent to an odd power, you rewrite all but one power of it as another trig function and then use a u substitution. If I were to give you something like a secant to an even power or a cosecant to an even power, you'd do something similar to this, but you'd make sure to leave two powers of it left over. Now, for the next portion here. Number 7 begins our problems involving trig substitution, which is not to be confused with integration problems involving trigonometry. Trig substitution is if you'll remember, is a problem which involves no trig functions at all in the beginning of the problem, and you change everything to trig functions, which is just a glorious idea in these problems. So when I'm looking at a problem like number 7 and I give you the integral of dx, now please keep in mind that I specifically say use a trig substitution to solve problems 7 and 8. I'm not saying that's the only way to solve these problems. In fact, it's not the only way, but you are supposed to know the technique of trig substitution. So I have to see trig substitution in these two problems in order to get credit. So trig substitution in problems 7 and 8, and I'll say, all right, as soon as I recognize in 7 that I have a variable squared minus a constant squared, then I'm thinking, well, this is where we let x equal a tangent theta. Now, if it were just x squared minus 25, it would be x equals, I said tangent, secant theta. Tangent is x squared plus a squared. This is x squared minus a squared, secant squared substitution. Now, had it just been x squared minus 25, you'd let x equal 5 secant theta. This, you can say, well, the group that's taking the place of the x squared here is the group 4x. So you'll notice what I did over here is I just said, let 4x equal 5 secant theta. That's because this variable portion here, you could think of it as the group 4x squared minus 25. So our trig substitution becomes, let the square root of this number equal the square root of this number times the secant of theta. Now, the trig substitution I'm actually making, though, is to solve for x and say, well, I would divide by 4 on each side, and x is going to be 5/4 secant of theta. Now, if I take the derivative of both sides and figure out what that numerator needs to be, dx, it's the derivative of this. So I can say, well, derivative of secant is secant tangent. So I'll get 5/4 secant theta tangent theta d theta. Then that square root in the denominator, the square root of 16x squared minus 25. That 16x squared, I know that that's just this term squared. 16x squared is the group 4x squared. 4x is equal to 5 secant theta. So 4x quantity squared is going to equal 25 secant squared theta. And then I have minus 25. And as soon as you do this, you can see, yeah, okay, this trig substitution is going to work nicely because I can factor a 25 out inside of that square root, and I would be left with secant squared minus 1. Secant squared minus 1 is the same thing as tangent squared. The square root of 25 tangent squared leaves me 5 tangent theta. Okay. So now I go back into my integration problem, and I can say then this original problem is equal to the numerator dx. That's my 5/4 secant theta tangent theta d theta. My denominator, it's that square root. I've already shown that the square root is equal to 5 tangent theta. So then at that point, 5/4 divided by 5, that gives me a 1/4. I factor out the 1/4. The tangent thetas cancel, and I'll have the integral of the secant of theta. Now, this is one of those that I will hesitantly give you on the test, although if you're working the homework problems, you probably saw that this one pops up a lot, and you probably already have it memorized by now. But the integral formula, I would give this on the test because it's a little tricky. The integral formula for the integral of the secant of theta d theta is going to be the natural log of secant theta plus tangent theta plus c. And again, I would give that formula on the test. Now, we're not done even once you get to that point, though, because you can say, well, that's the answer with respect to theta. I need the answer with respect to x. So I can say, well, all right, then I create a trig triangle. That trig triangle is generated by your initial trig substitution. 4x is equal to 5 secant theta. which means secant theta is equal to 4x over 5. I draw my trig triangle. I know secant is nothing more than the reciprocal of cosine. Cosine is the ratio of adjacent to hypotenuse. So the secant's the reciprocal of that. It's hypotenuse over adjacent. So when I draw my trig triangle, I need to make sure that the hypotenuse of the triangle is 4x. The side adjacent to theta has to be 5. That means the other leg of your triangle has to be the square root of the hypotenuse squared minus that leg squared, square root of 16x squared minus 25. And no surprise, the expression from the original problem always has to pop up in your trig triangle. If it doesn't, that's a clear sign that you've done something wrong. Now, I go back in and I solve my problem. I'll get 1/4 natural log secant theta. Well, we already knew secant theta was 4x over 5. You don't even need your trig triangle for that. It was our trig substitution. So secant theta, 4x over 5, plus the tangent of theta, that would be plus opposite over adjacent. So we have our square root of 16x squared minus 25 over 5. And I am fine with this answer right here. For those of you working with Achieve, you'll know that they like you to absorb as much into the constant of integration as possible. So again, I am perfectly fine with this answer. But what you could do here is you could say, well, hey, this is equal to 1/4 the natural log of 4x plus that square root of 16x squared minus 25 all over 5 inside of that natural log. And then whenever you have that, you can say, well, if I have a quotient inside of a natural log, then that's the same thing as the natural log of the numerator of that quotient minus the natural log of the denominator of that quotient. And you're like, well, but you didn't put that. Well, I did, because the denominator of that natural log, it's just a constant. You'd be saying minus 1/4 natural log of 5. Minus 1/4 natural log of 5 is just an irrational number. That irrational number gets absorbed by the constant of integration. Do you have to do that for my test? Absolutely not. But I thought I would mention that since those of you who are using Achieve have had to do that on several problems on Achieve. The answer I'm perfectly fine with is this one right here. This one right here is fine too, though. Number 8. Number 8 is our last of the trig substitution problems. You'll see in this one, I gave you a problem where you had the variable squared minus the constant squared, so you knew that was our secant substitution. The next one, you have a constant squared minus a variable squared. You're supposed to remember, oh, this is our sine substitution. I will let x equals 6 sine of theta in this problem. The only other one that you might have to keep in mind is what if it's x squared plus a squared? That's where you let x equal a tangent theta. For number 8, I knew it was a sine substitution because of the 36 minus x squared, so I'll let x equal 6 sine theta. Dx is the derivative of that, 6 cosine theta, d theta. At that point, I know my numerator is already going to be 36 sine squared times the dx, the 6 cosine theta d theta. I need to show what the denominator is equal to. That denominator, that square root of 36 minus x squared becomes the square root of 36 minus x squared is going to be your 36 sine squared theta. At that point, you factor out the 36 on the inside of the root, and you'd be left with 1 minus sine squared. We know 1 minus sine squared is equivalent to cosine squared. So that square root becomes the square root of 36 cosine squared theta. Square root of 36 cosine squared theta, 6 cosine theta. I've showed what my denominator is. So at this point, I go back into my original problem and say, well, it's just equal to the numerator, x squared, which is your 36 sine squared theta, times dx, 6 cosine theta d theta, all divided by the denominator, 6 cosine theta. Well, clearly the 6 cosine theta part cancels, and you should always expect something to cancel out in these trig substitution problems, and it does. And then I'm left with 36 sine squared theta. I can factor the 36 out. And then you say, well, hey, we already had a power reduction problem with the fourth power of the sine function earlier on this practice test. Here I have the power reduction formula with sine squared. No big deal. I know that sine squared theta is equal to 1 minus the cosine, or sorry, 1/2 times 1 minus the cosine of twice the angle. That 1/2 came out, multiplied the 36 to give me an 18. And then 1 minus the cosine of twice the angle. Okay, now at that point, I'm able to integrate. The integral of 1 with respect to theta is theta. The integral of the cosine of 2 theta becomes the sine of 2 theta over 2. So minus cosine 2 theta becomes minus 1/2 the sine of 2 theta. But here's where you say, well, I can't have that sine of 2 theta though, because I need my answer back in terms of x. If I don't have my angle in terms of theta, I'm not able to get it back in terms of x. So here's where you had to use your double angle identity and say, yes, but the sine of 2 theta is equal to 2 sine theta cosine theta. And the 2 from that cancels with the 1/2 out in front. And so we just have 18 times the group theta minus sine theta cosine theta, of course, plus your constant of integration. So then I can say, well, all right, I have my answer, final answer in terms of theta, but I need my final answer in terms of x. So theta, that's pretty easy to work with. I can just look at my trig substitution and say, well, x over 6 would equal the sine of theta. So theta would equal the inverse sine of x over 6. That's where that first part came from. The second part, though, involving the sine and cosine, I knew I'd need my trig triangle. I used this same trig substitution to set up my trig triangle. Knowing that the sine of theta is x over 6 tells me that the opposite side from theta is x, the hypotenuse is 6, which means the other leg, the adjacent side to theta, has to be the square root of the hypotenuse squared minus this leg squared. So we get 36 minus x squared under the square root for that other leg. Now I go in and I can say, all right, 18 times the group theta, we've already discussed, theta is going to be the inverse sine of x over 6, minus the sine of theta, which obviously x over 6, times the cosine of theta, which will be adjacent over hypotenuse. That's the square root of 36 minus x squared over 6. Now just cleaning this answer up, I distributed the 18 through and got 18 inverse sine of x over 6. My second term would have had a denominator of 36, but I'm multiplying it by 18. So 18 over 36 gave me minus 1/2 x on that square root of 36 minus x squared, plus your glorious constant of integration. Okay, I'll do the remaining problems in a second video just to make sure Zoom doesn't cut me off for going over time extensions.